All right, let's jump right into this. Welcome to this explainer. Today, we are stepping straight into the ring for an absolute tactical masterclass on Cambridge mathematics. I want you to think of the exam room as a boxing ring. In this ring, your answer combinations, the way you string together your logic, your working, your final presentation, literally mean the difference between a knockout victory and getting knocked out yourself. To really understand how to win this fight, especially when it comes to the notoriously tricky topic of graphical solutions for syllabus codes like 0580, 0606, 4024, 4037, and 4040, we need to look at a classic student showdown. Imagine we have a real Cambridge past paper question right in front of us. On the left corner, we have Alex. Now, Alex is a hard worker, no doubt about it. But Alex's approach? It's like throwing wild punches. Alex overloads the answers with raw, unfiltered mathematical facts, listing everything under the sun, but completely lacks structured analysis. There's no strategy. And in the right corner, we have Sam. Sam's problem is different. Sam sees the clock ticking, panics, rushes through the calculations, and completely misses the specific command word requirements in the question. Today, we are going to look closely at these two flawed approaches. We'll see the red pen marks all over their papers, and we are going to transform those mistakes into perfect, top-tier, green checkmark responses. Float like a concept, sting like evidence. Let's dive in and build your ultimate combination.
Okay, so here is our structured playbook for today's session. We are going to cover the accuracy challenge, followed by core graphing principles. Then we'll look at some critical examiner warnings, move into the procedural framework, and finally, we'll lock in the systematic success strategy.
Section 1. Let's talk about the accuracy challenge. Now, we are anchoring our entire strategy today on one specific phrase, straight from the Cambridge syllabus. It says, for graphical solutions, an accurate graph is expected. Look, I know what you're thinking. Obviously, it needs to be accurate. It sounds incredibly simple, doesn't it? But trust me on this, it is actually the single most misunderstood and poorly executed area in additional mathematics. When the examiners use the word accurate, they absolutely do not mean a line that just vaguely points in the right general direction. Accurate is a heavily loaded command word. It demands a rigorous, uncompromising precision. We are talking about using mathematically sharp pencils. We are talking about precise plotting using fine crosses instead of thick, messy dots that cover half a square unit. It means choosing an appropriate scale that maximizes the given grid rather than cramming your entire graph into a tiny corner of the page. And it means drawing a mathematically sound line of best fit that perfectly balances the coordinates. Think about it as a domino effect. If your initial graph isn't strictly accurate, what happens? Your subsequent calculations to find the gradient are wrong. Your y-intercept is wrong. Your final contextual answers are going to be completely off. It triggers a devastating chain reaction of lost marks across the entire question. You lose the fight before you even throw the second punch.
So, this begs the question, why do students find multi-stage analysis and securing those vital method marks so incredibly hard? Why is it such a struggle? Let's bring our contenders, Alex and Sam, back into the spotlight. When faced with a complex, multi-stage graphing question, let's say they have to convert a nonlinear relationship into a linear straight-line graph using logarithms, Alex goes into overdrive. Alex writes down half a page of scattered algebraic facts, randomly manipulating logs and exponentials without any chronological step-by-step analysis. It's a superficial breadth of knowledge that completely misses the target of what the examiner is actually looking for. There's no narrative to the math. Sam, on the other hand, sees the command word evaluate or show that, immediately panics, rushes the plot, draws a sloppy, heavy-handed line of best fit, and just scribbles down a final number. Sam completely skips the crucial intermediate steps and misses out on a massive pile of method marks. They are both just throwing wild, uncoordinated punches in the dark. You see, multi-stage analysis requires systematic processing. Your brain is dealing with a lot of data at once, and without a strict, unshakable framework to guide your hand, you simply get overwhelmed. You need a system to rely on when the pressure hits.
Section 2. Let's establish the core graphing principles. The absolute foundation of your entire exam technique must be built upon the method mark strategy. What does this mean? It means actively earning marks through logical, structured reasoning and transparent analytical processes, rather than just trying to magically arrive at the final mathematical answer. Cambridge examiners actually reward the analytical journey you take. They want to see your brain working on the page. To achieve this level of clarity, top students use a specific framework. Now, you might have heard of the Peel framework in your essay subjects: point, evidence, explanation, link. Well, guess what? It is a total knockout blow in mathematics too. It is how you guarantee every single method mark. First, the point. You explicitly state the mathematical principle or the equation format you are using, like y equals mx plus c. Second, the evidence. You extract the precise coordinates or data directly from your accurate graph. Third, the explanation. You show your clear step-by-step algebraic working to calculate that gradient or that intercept. You literally explain the math through your steps. And finally, the link. You tie your numerical answer back to the specific context of the original question, like defining what the constant A actually represents in a physical model. This framework is your ultimate defense and offense. Now, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. This comparison perfectly illustrates the difference between our two approaches, and frankly, the difference between an average grade and a top-tier grade. On the left side, we have superficial breadth. This is exactly what ALEKS does. It involves just listing disjointed mathematical facts and formulas, hoping and praying that the examiner will do the hard work of piecing them together. But examiners aren't there to connect the dots for you. On the right side, we have analytical depth. This is what the Cambridge syllabus actually demands from you. It requires structured reasoning, establishing clear causal relationships, and using precise and unambiguous definitions. Analytical depth proves to the examiner beyond a shadow of a doubt that you understand exactly why the mathematics works in this specific scenario, not just how to punch random numbers into a calculator. It's the fundamental difference between handing the examiner a scattered, confusing puzzle and presenting them with a beautifully constructed, solid mathematical foundation. When you use analytical depth, you are controlling the flow of the entire exam.
If you want to break into those absolute highest grade boundaries, we have to elevate your cognitive domain. Let's break this down. At the descriptive level, you are just demonstrating basic knowledge. In the context of graphical solutions, this is merely plotting your points accurately on the grid. Now, don't get me wrong, it's absolutely necessary, but it is only the first step. It won't get you an A-star on its own. Moving up to the analytical level, this is where you start establishing causal relationships. You've drawn your perfect line of best fit, you've deliberately selected two distant points on that line, not from the table, but from the line itself, and you are actively calculating the gradient to uncover the hidden relationship between the variables. Finally, we reach the evaluative level. This is what secures the distinction. Here, you are providing justified recommendations or conclusions based on your math. You aren't just writing down that the gradient is 2.5 and walking away, you are evaluating what that 2.5 actually signifies within the given real-world context of the question. You are translating the mathematical abstract back into concrete reality.
Section 3. We need to talk about critical examiner warnings.
Okay, this is where the transformation really happens. We are going straight behind the curtain to look at the top mistakes pulled directly from the principal examiner reports. Even mathematically brilliant students bleed marks here if they ignore these 3 critical warnings. We are going to take the red pen marks off Alex and Sam's papers and turn them into green check marks. Warning number 1, confusing cause and effect. In graphing, this incredibly common mistake usually means plotting the dependent and independent variables on the completely wrong axes. If you mix up your x and y, your entire analysis collapses. Warning number 2, forgetting to check format and presentation conventions. This is Sam's absolute biggest flaw. When you finish plotting, you have to ask yourself, did I clearly label both axes with the correct units? Did I explicitly state the scale I used if the question asked for it? Did I write down the exact coordinates of the points I used to calculate my gradient? If you don't present the math clearly, you don't get the marks. Warning number 3, providing answers that are not specific to the given context. This is where Alex falls short every single time. Imagine a question asks about the initial velocity of a particle based on a kinematic graph. If you do all the math correctly but just write v equals 5, instead of explicitly writing initial velocity equals 5 meters per second, you will drop the final accuracy marks. Why? Because you completely failed to link the abstract mathematics back to the physical reality of the problem. And I want to highlight this massive, flashing red flag straight from the examiners. They write, candidates consistently confuse key terminology, always define terms. Listen, if you are tackling a complex nonlinear equation and you are introducing a logarithmic transformation to create a straight line graph, you cannot just start drawing. You must clearly and explicitly write down what your new capital X and capital Y axes represent. If capital Y is log Y, you write that down. Do not make the examiner guess your intentions. Now, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Section 4. Let's map out the procedural framework. It is time for an interactive workshop.
We are going to systematically walk through this exact 5-step sequence. This is your ultimate blueprint for executing complex graphical solutions under immense time pressure. Step 1. Deconstruct the question. Before you even touch your calculator, underline the specific command words. Are you being asked to find, evaluate, or show that? Those words dictate your entire strategy. Step 2. Extract relevant data. Let's do a 60-second data scan challenge in your head right now. Imagine a complex data table on the page in front of you. Do you need to calculate logarithmic values for every single entry before you can even begin to plot? Yes. You have to scan, identify the trend, and prep the data first. Step 3. Select the analytical framework. This is the exact moment you deploy the peel method we talked about earlier to tightly structure your logical thought process. Step 4. Execute with clear notation. Now let's play Find the Flaw. Imagine a paragraph of working out where someone just writes down a final gradient without showing the fraction they used. What's the flaw? The examiner cannot mark your invisible thoughts. You must show every single line of algebraic working. Step 5. Present with correct terminology. Bring the whole thing home by explicitly stating your final answer in the exact format, units, and significant figures requested. Let's dial in on Step 5 for a second. Think back to Sam. Sam rushed the presentation and hemorrhaged easy marks. To ensure you completely avoid Sam's fate, you must adopt these strict presentation conventions right here. Let's do a 30-second mental speed writing challenge. Visualize your perfect graph. First, you need clear annotation. You should draw a highly visible, appropriately sized triangle directly on your grid to show exactly which 2 points you are using to calculate your gradient. And remember, those points should be as far apart as possible to maximize your mathematical accuracy. This visual proof instantly shows the examiner that you are in total control of the data. Next, proper headings. If you are making a new table of values for your transformed coordinates, label the columns clearly. And finally, appropriate formats. This is crucial. If the front of the exam paper demands 3 significant figures and you give 2, or you leave it as a messy, unsimplified fraction when a decimal was expected, you are giving away free marks. Precision is everything in this ring.
Section 5. Bringing it all together into the systematic success strategy.
Now, sometimes these higher-level graphical solutions questions will require you to compare 2 completely different mathematical models or data sets on the same grid. The crucial point here is knowing exactly how to handle comparative analysis. Do not, under any circumstances, fall into the trap of only listing how the graphs are similar. You absolutely must identify similarities and differences. To do this effectively, use powerful comparative connectives in your written explanations, words like whereas, conversely, or indirect contrast to. But here's the most important rule. You must support every single comparative claim with hard numerical evidence extracted directly from your accurate graph. Don't just make a vague statement like, graph A is much steeper than graph B. That's descriptive, not analytical. Instead, you need to say, graph A demonstrates a significantly greater rate of change with a calculated gradient of 4.5, whereas graph B's gradient is only 1.2. Finally, you draw clear, contextual conclusions on the relative importance of these mathematical findings.
For those of you aiming for the absolute top marks, the A stars and the top-tier distinctions, you need to master highest order evaluation. The best mathematicians in the world don't just blindly calculate, they actively critique their own models. Think about it. When you draw a line of best fit through experimental data, you are inherently making an assumption about a trend. To secure those highest-tier evaluative marks, you must be prepared to identify the limitations of the mathematical model you just built. For example, the examiner might ask if it's mathematically safe to extrapolate your graph, to extend your line to predict a value far outside the range of your given experimental data. Usually the answer is no, because you are making a massive assumption that the linear relationship continues indefinitely without changing. Actively questioning these built-in assumptions and intelligently evaluating alternative interpretations of the data is exactly what separates a good, hardworking student from a genuinely top-tier Cambridge scholar. So let's lock in our final foolproof processing sequence to guarantee your success. Rule 1, command word decoding. Identify the key elements and know exactly what is being asked. Rule 2, peel framework application. Apply relevant principles logically and execute your analysis with crystal clear working. Rule 3, time management matrix. Verify your results efficiently and always present them in the exact appropriate format. In the exam room, an accurate graph isn't just a suggestion, it is your definitive, unquestionable path to victory. So ask yourself, the next time you sit down with a complex, multi-stage data set, will you just blindly plot points, panic, and rush the process like Alex and Sam? Or will you use this system to command the data and force it to reveal its answers? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to at Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.